Hello everybody, I am Mohsen Mahmoudysepehr, PhD student and Center for Advanced Photovoltaic Devices and Systems under the supervision of Professor Sivat. Today I'm going to present our research about the semi-transparent nanocrystalline silicon thin film solar cell, mainly under the Network Project 12 for the application as a building integrated photovoltaics. First of all, I'm going to talk about the transparent solar cell and some idea behind that. The main idea is that we need to develop a transparent conductive layer since we want to be a transparent and assure that it's a very high quality, very high transparency. We choose the zinc oxide for this application due to the cost effectiveness of this layer and also achieving very good transparency in this respect. Also, our second target is to developing a transparent dope layer and also very good observer layer based on amorphous silicon or nanocrystalline silicon layer. And at the end, we try to integrate our previous finding on the conductive layer and the transparent doped and observer layer to a device integration and fabrication of the final cell. First of all, in order to give an idea regarding the application of the thin film and also thin film devices, here I have simulated the optical absorption of the different layer to compare it with microcrystalline silicon, a 2 microcrystalline silicon with the blue. A red one is a 300 nanometer amorphous silicon, 200 nanometer and 100 nanometer amorphous silicon. It is a simulation based on passing of light among these layers with one passing without any reflection. We just want to see that if it is an ideal device, ideal layer, what is the optical absorption. And as we see, 200 nanometer and also 300 nanometer amorphous silicon look like the absorption is the same. And also, we have lots of space for the improvement of device in the IR part by applying some sort of advanced light trapping technique or the other things. We could make use of these part of the high wavelength spectrum that they didn't provide any contribution in the optical absorption. This shows us specifically 200 nanometer layers are very attractive for this application. So, all the thin film, the main reason that we want to work for them is the transparency. And the second and the third reason is that by decreasing the thickness of the observing layer, one advantage is that we could increase the open circuit voltage by the relation that we know. Actually, it seems that it's changed by the presentation here on the Mac computer. Anyway, since we decrease the thickness, the dark conductivity or the dark current is going to decrease. And by decreasing the dark conductivity, we could have the increase of the open circuit voltage by logarithmic relation. But we must pay attention to something else as well, since we want to reduce the recombination center as well, because if we don't get rid of this recombination center, the photocurrent is also going to be low, and that's going to affect the final efficiency of the device. So at the same time, by reducing the thickness and by improving the quality of the layer in respect to the open circuit current, we could expect acceptable efficiency devices. Okay, at the first stage, we decided to develop a good layer of aluminum-doped zinc oxide in order to achieve very reasonable efficiency. The main aspect is that we need to at least below 10 ohm per square conductivity in order to have a very good field, at least as an acceptable level, as an acceptable conductive layer. For this reason, we try to manipulate these conditions by changing the pressure of the sputtering system that decided to use and changing the RF power to reach to a reasonable condition at room temperature. Then we are going to apply this condition at higher temperature to reach at least an acceptable level. In the above diagram, we will see the effect of the pressure of the sputtering system in respect to the RF power on the resistivity of the deposited film, and we find the two conditions with the lowest resistivity, although it was above 10 ohm per square. But we reached to this condition, and then we apply these two conditions by increasing the temperature, and we reach to the reasonable level of around 5 to the minus 10 to the minus 5 times 10 to the minus 4 ohm per square. Although this 5 is still below 10, but we know that it is not very good, since the record is already 3 times 10 to the minus 4. By improving the condition a little more, right now we are at the level of 3.5 times 10 to the minus 4. Actually, it's not indicated in this diagram since we just last week reached this record. And we believe that by further working on the condition, specifically applying some controlling the grain size of the aluminum doped zinc oxide, we could reach to below 3 as well and reach to a level of around 2 times 10 to the minus 4, which is very good as a conductive layer. Here is the transparency of the developed film. As we see, without any difficulty, we have higher, about 80% transparency for the layer, which is very good. At the second level, we decided to develop the doped layer for the solar cell that is, we want to work on it, since it is based on a single junction PIN structure. We try to develop an N-type nanocrystalline silicon. Since it is some sort of behavior of crystalline silicon, we could expect that we have a higher conductivity, and also light-induced degradation is low because we are away from amorphous condition that cause the SW effect to decrease the efficiency of the layer. Right now, by controlling the ratio of the phosphorus gas to the silane, we reach the maximum condition in respect to the higher conductivity. And right now we have the 17S over cm conductivity for 51 nanometer thickness layer, which is very good, and we don't actually have any problem. Here is the Raman spectrum spectroscopy for the developed layer, and show clearly the nature of the non-crystallinity of the developed layer. The big challenge for this project was developing the p-doped, or let's say boron-doped layer, since there are lots of issue in the boron-doped nanocrystalline silicon. First of all, is that boron is the boron doping concentration is really low, between 10 to 20%. Also, the nature of nanocrystalline hydrogenated layer is some sort of N-type behavior. So when we want to deposit a p-type layer on top of it, we must neutralize this rail, and that's making another difficulty by depositing the p layer. And the other problem is the catalytic reaction of boron with hydrogen, which somehow enhance the loss of surface of hydrogen, and the crystal growth of the layer is going to be changed and be moved toward the became the amorphous layer instead of the nanocrystalline layer. Right now, by controlling the hydrogen dilution ratio, the ratio of the boron to the silane ratio, and the controlling the pressure of the PCVD chamber, we reach to a P layer with the conductivity of 0.04 S over cm conductivity. Although it is not very good, but right now we are at this level and we try to make it better. Actually, one of the future works is going to improve the quality of the P layer. Regarding after we develop the P and N, we just try to work on the nanocrystalline silicon observer layer. At different silane ratio, we try to reach to a condition that we reach to a nanocrystalline layer. We see that by changing the silane ratio, we could change the condition of the crystallinity, and at what ratio we could have a nanocrystalline one. Here is the transparency of the developed I layer, and we see the very acceptable transparency for this one. And in order to enable the non-crystalline behavior specifically for a condition that we have a good conductivity, the main reason is that we must have a behavior of a layer with the condition between amorphous and complete crystalline. This layer, which normally known as a prototype silicon layer, or I would like to call it a non-crystalline silicon, has the best condition in respect to conductivity, optical absorption. By controlling the silane ratio, hydrogen to the silane ratio, we could achieve this. By the previous developed layer, we make a cell and measure the short circuit current, and by changing the silane ratio, and we find the maximum level of the silane ratio in order to we have a very good short circuit current. After developing this layer, we just fabricate our cell here. is the structure of oxide, which is a single PIN on top of the glass with the aluminum zinc oxide as a conductive layer. Here is the result of the external quantum efficiency and the IV characteristic of the developed layer. We have developed 300 nanometer and 200 nanometer amorphous silicon and 200 nanometer nanocrystalline silicon with the efficiency of the amorphous silicon around 6.5 and for the 200 nanometer crystalline and amorphous is around 5.5. Here we see the external quantum efficiency and some sort of improvement for the UV part of the light in the nanocrystalline part in respect to the IR part of the wavelengths for the amorphous silicon. Due to the transparency issue, we just stick to a 200 nanometer amorphous silicon and we avoid 300 nanometer development. Here is the final cell that we have fabricated up to now with above 45% transparency, and the best condition that we reach up to now is the open circuit current around 740 millivolts, the short circuit around 11 milliamps, and the efficiency 5.5. Right now, we need to improve the shunt resistivity because we believe that one of the main issues is the field factor improvement, and we need to improve the shunt resistivity of our devices by improving the recombination, or let's say the quality of the specifically P layer, and a little improvement in the I layer. We also need to improve the our contact conductivity right now because we are at the 3.5 10 to the times 10 to the minus 4 region, and we believe that by the new method that we are going to develop it in the next month, we could reach to around level of 2, which is very good in respect of conductivity, and we could improve these shunt resistivity that exists and avoid very high efficiency. And at the end, after we improve the layer, we are going to apply the light trapping techniques to incorporate the part of the light that we never absorb in the light. In this cell. As you remember in the first slide, the IR part of the wavelengths was never incorporated in the current. That's why we are going to design a specific light trapping techniques in order to use that part of the light, which is not affecting the transparency, but it will definitely help us in order to improve the total efficiency of the device. At the end, I just want to thank my group members. This project was not done by me. Actually, other group members of the Center for Advanced Photovoltaic Devices was involved. Dr. Sanullah Fatih, Mr. Navid Jahed, and Ms. Lintian was also incorporated because, as you see, it was a three somehow different parts: development of the conductor layer, development of the dope layer, and the device integration. Thanks for the NSA for providing and supporting this project, and also the Photovoltaic Innovation Network. And here is the final summary of my achievement, which I explained before, just developing a very good conductive conductor layer, developing the nanocrystalline dope layer and the absorber layer, and the final device right now at these two conditions that we need to improve it by our further research. Thank you very much for your attention.